Okay, it's time to start. Welcome everyone at our weekly colloquium. Our speaker today is our own Dr. Wojciech Hellwing, and he will tell us why and how to test gravity. Please.
On cosmological scales.
On cosmological scales.
If I can add it. Good afternoon, ladies and gentlemen. It's a great pleasure to finally deliver a CFT colloquium or conversatorium, or it used to be called seminar, although I already given one, I believe it was 2016, roughly on a little bit similar subject, actually closely related subject, but I will now show you much broader perspective as the colloquium should require, or conversatorium on the topic, with some my own results only be present at the very end, when I hope I can convey them in a very straightforward manner. So the test is why and how test gravity, but actually there should be theory of gravity, because gravity, it's not a natural phenomenon, but we need a theory of this phenomenon to test it somehow. So first I'll give you an outline, because I hope I can fit everything in 50 minutes. I'll give you a very, very average introduction to standard model of cosmology, because this is going to be a talk about testing gravity on the largest scale compared to everyday tests we think, like on solar system scales. Then a very basic thing about general relativity, which is our working theory of gravity in a standard model of cosmology. So basic and current status. Now I'll tell a little bit about beyond GR. Why would you like to consider going anywhere beyond GR if GR works so well? And if you would like to do it, how you can do it. So this is more or less modified gravity, a very growing and vivid field in the cosmology nowadays. An important part will be about modified gravity screening as a special mechanism, theoretical mechanism, many different ones that were discovered during the development of various theories that allow to suppress propagation of extra degrees of freedom, which most of these theories involve, in the vicinities of bodies like Earth, because otherwise all tests of gravity we have from solar system would immediately falsify all these modified gravity theories. So there's a screening mechanism. And this is the biggest, well, it's a pinnacle of these theories, because the screening mechanism is very nonlinear, which makes the conveying tests of such theories more complicated. Now I will tell you a little bit about what could be observational effects of beyond GR theories, so all these modified gravity theories, and also of self-consistent testing GR. Troubles, of course, because things wouldn't be interesting if they would be easy, and then outlook for the future. So let me start with a standard model of cosmology, which is rooted in very core assumptions. And all of these assumptions, for a standard physical theory, should be tested rigorously every day with new ideas of how to test them, because we're doing empirical science, not philosophy, of course. So we assume that the universe started with the hot relativistic Big Bang. There are many predictions the universe had to be hot and very small, close to the singularity. Maybe you could avoid initial singularity. Nevertheless, the physics doesn't reach the initial singularity of the Big Bang, but there are many predictions from this period of time of the universe history, like primordial abundance of primordial elements, or cosmic microwave background radiation, and so on and so forth. Now we also assume that all fluctuations and structure we see now in the universe arose from some tiny primordial initial fluctuations. You need a mechanism that sits otherwise uniform density of every field energy and all the tensor fields you could put in the universe. So we assume that the inflation, as the only hypothesis, but it's quite a strong one, at least plausible one, inflation produces adiabatic Gaussian initial conditions. So the initial conditions, fluctuations that's supposed to come from the vacuum fluctuations, zero-point energy vacuum fluctuation from before the inflation, when the universe was smaller than the atomic size of an atomic molecule, were then stretched out to the larger scales and imprinted in the energy tensor of the universe. And they're adiabatic, and because there was a Gaussian process, they have Gaussian nature. So basically, you only need variance and the mean to describe these fluctuations. Now, we also assume that the universe can be described using two simple symmetries. So we assume global homogeneity and isotropy. And the word global is very important, because obviously, locally, the universe is neither homogeneous nor isotropic. The specific directions, like towards the galaxy, for example, when we have a radial acceleration, or local density fluctuations like this bench, of course. But if we go to the grand scales and more or less we understand those scales to be around 100 megaparsecs nowadays, so 300 million of light years. The universe really appears to be homogeneous and isotropic. Thanks to these two properties, we can build a background model of the universe using general relativity, and then this simplifies many things a lot. But this is still an assumption that is, of course, being tested every day. So in the universe, definitely this looks very good. So in the universe, we have CMB, for example, fluctuations from the hot Big Bang that are very uniform and very isotropic. By very, I mean they uniform to the extent of one part in a 100,000. So this means, to put it in the scale, if the Earth surface would be of this uniformity, Mount Everest would have 30 meters. So this is very, very small fluctuations. If in the late time, I mean late universe around us, this is still under the scrutiny, but I said 100 megaparsecs more or less looks okay. Okay, something is missing here. Okay, dominant component of matter is dark matter. It's good that was invisible matter, and now it was detected with very high significance, statistical significance in the cosmic microwave background radiation. I think I talked a little bit about this during one of the report session of our institute's fundamental research tasks. I won't talk about dark matter today, but we still have to remember that its physical nature is unknown. We assume this is some elementary particle created in the early universe when the universe was very hot. We have idea roughly what it should be, its basic properties to match all the observations, but we still have the problem that our colleagues from Large Hadron Collider in Geneva couldn't find, or in many different other way, ground-based detectors didn't find a particle like that. Nevertheless, we see the dark matter pervades the universe. It affects strongly the structure formation, and without this component, we couldn't either explain the patterns we see in the cosmic microwave background radiation or galaxy formation whatsoever. Finally, the last core assumption is that general relativity is the theory of gravity on all scales. But we have to remember, and I will say something more about this in a few minutes, that this theory, even though it's beautiful and very powerful, has not been tested to its full extent to the whatever you can think about what would be this theory parameter space. And usually, I didn't have this slide on this kind of talks before. I used to have this slide many years ago when I was a still PhD student, but I would now put it back. And this slide is basically, okay, I'm going ahead a little bit of myself. Sorry, I think, okay, I will skip this. I will go back in a moment. So this is the slide. So this is quotation from Jim Peebles, who addressed General Assembly of International Astronomical Union in the year 2000. I will read this with quotation. The elegant logic of general relativity theory and its precision test recommends GR as the first choice for a working model for the cosmology. But the Hubble length is 15 orders of magnitude larger than the length scale of the precision test at the astronomical unit and smaller. So we have a spectacular extrapolation. And now we know this is Nobel laureate, so many people, maybe this argument adds some weight. But to be more serious, why we should think about modifying gravity? I think we have three main components to this question. First, there's a theory challenge, which means that we can, basically. And what freedom is there to create a consistent physical theory of gravity other than general relativity? It's a very interesting question. GR has its own limits, right? For example, prediction of black holes when the theory breaks down. What happens in singularities? Or why we cannot quantize the gravity using general relativity as a theory, working theory on the low energy or large scales. Now there's also experimental challenge. We must test the extrapolation of this physics from the solar system to the whole universe. This should be 10 to the 15. I will tell more about this in a minute. And then also we have observational challenge, which is the following. What is responsible for this observed cosmic acceleration? In the standard model of cosmology, we assume is the Einstein cosmological constant, which is a very good assumption. But of course, the very small value of this observed constant is unnatural if you would involve standard physics arguments. So we've been there here? Okay.
Why smallness of this constant is unnatural?
It's unnatural because there's no symmetry. Like, for example, let's go to quantum fields. If you have if you consider chiral symmetry, it protects the mass of electron to not get arbitrarily large, because it will be proportional to the perturbations of this mass will be proportional to the 0-point mass. So once you set electron mass to be small, it will always stay small. There's no symmetry like that that would protect Einstein cosmological constant to remain small. Even if you set it to be very small, the quantum correction get arbitrarily large, because there's no symmetry protecting the quantum correctness. So in this sense, it's a de Hooft sense of unnatural value to be small.
It sounds too entropic that it's related to our understanding, but it is not really built into nature.
I fully agree with this. It's a weak argument. Nevertheless, it doesn't falsify this consideration, because we should always go beyond. This is part of, this could be universal nature, constant of nature, and there should be difficulty to understand this on quantum level. Nevertheless, this is one of the simplest possible scenarios. We should go beyond, and I will explain why this is very important. So a very quick recapture.
Indeed, what you mentioned was a prevailing view maybe 20 years ago. And people, that was one of the most main arguments to build Large Hadron Collider, because people thought we need supersymmetry. Supersymmetry would solve a lot of those problems. But apparently there is no
Sign of supersymmetry.
And maybe it's time to rethink this philosophy, actually, that symmetries are mechanisms which protect values to be as they are. We are searching in the dark at the moment.
Well, of course, literally we're searching in the dark in astronomy, but also we are in the dark when it comes to the theoretical physics. So of course, we on the cosmology side, observer side, waiting for the breakthrough theory. I will explain also that the modified gravity theories I will briefly describe today, none of them will pretend to be new fundamental theory of gravity. They're just small, minute variation, what is allowed. But so they are basically effective phonological theories, because we, at the present, don't have any single beautiful theory, strong theory that will be trying to compete with GR. So they are kind of a little bit of epicycles, but I will still try to convince you that there is a point looking for those, because we need to look for the cracks in any physical model that describes world or universe we have, to look for the new physics. So just very quickly, general relativity is the metric theory. So Einstein field equations can be derived by varying Einstein-Hilbert action integral with respect to metric. So we have GR curvature term. We have, of course, standard model particles and dark matter, because we need to populate the time-space with matter. And then we have Einstein cosmological constant. That's a basic GR. And then paying attention, all these G's here are metrical space and time. And now we also have Lovelock's theorem that says that this formulation of GR is the only possible formulation that will give you only second-order differential equations for the metric perturbations. And now, of course, this was absolute breakthrough. It was formulated by Einstein more than 100 years ago. But I think it's also illustrative for this particular talk to put in context how this theory arose and what was also essential, what was the picture when the theory came into place nearly 100 years ago. So I would say paving the way to new paradigm. So in 19th century, the Newtonian physics was at its best. It was really triumphing. You could describe motions on solar bodies, not only solar bodies, even smaller bodies. And it was used even to predict new bodies in the solar system with a success. For example, in 1895, Urban Le Verrier, it was actually previously than 1895, Urban Le Verrier, I think in 1849, he postulated that the observed perturbation of Uranus orbit can be explained if one assumes dark perturber, another massive body that will be farther away, that will perturb Uranus' orbit. And of course, this body was discovered. Actually, the Le Verrier predicted the location of this body using the simple Newtonian mechanics. And only after 2 hours, it was discovered by the German astronomers, unfortunately, whose name I don't remember. So it was Neptune. So this idea of testing theory of gravity was actually already having a success. So a few years later, Urban Le Verrier, there was a French mathematician, showed that slow precession of Mercury's orbit, perihelion, could not be explained by Newton's theory of gravity. So there was this observed precession of the perihelium, so the innermost close to Sun point of Mercury's orbit. So he proposed a conjecture, hypothetical planet Vulcan as a cause of this anomaly. Because he tried to use the same logic he already used for predicting Neptunes, which was successful. So there should be a low vulcanoid zone when there should be another very small rocky planet orbiting around the Sun. It would perturb orbit of Mercury and therefore explain this observed phenomena. As we know, Vulcan was never discovered, and we have a very, of course, good observational constraint. There's no planet in between Mercury and Sun. Instead, we know the Newtonian theory had to be improved because so close to Sun already, gravitational field is strong, and the Newtonian theory start to be poorer and poorer approximation to physical reality. So we had to introduce Einstein general relativity. And actually, I think it was this argument that the Einstein proposed general relativity and was completely new, radical view of the world, and immediately it could explain this anomalous perihelion. Later, of course, also it explained the twice as large as Newtonian predicted angle of deflection of the stars around close to the solar surface. Was very important to Einstein himself. So it's from popular culture Star Trek series, and this is one of the most famous characters from the alien race that comes from the planet Vulcan. So that was just a passing. So this is I'm just showing this to stress out that it's very important to test theories on all possible scales and length in parameter spaces. So Newtonian theory was looking great in the weak field limit, like around far away from the Sun. It was giving great predictions that lead to new discoveries. Although we found its limit, and Einstein theory, which is a more general theory, better theory of the universe, explained this phenomena. But we wouldn't know it, of course. In the GR case, Einstein would come up with the GR nevertheless. But this is important, I think, not this point to take that. We are physicists, so we should continuously put every theory under scrutiny.
Since you are talking so much about it, can I make one comment?
I'll get priority to the lady.
It's really impressive precision, which we already had at that time, because actually 90% of the Mercury precession is explained.
Yes.
It's only 10% of the precession which was less than 10%.
Just a minor remark. General relativity was not conceived in order to fit those data.
No, of course.
But because the Newton theory of gravity was incompatible with special relativity, and this was the only way to somehow make the picture consistent.
Of course, I simplify a landscape a lot.
And of course, these observations made by later in 1919
By Eddington expedition.
were important to show that this idea was intelligent. However, the beginning of general relativity
Right. Of course. But my point.
make physics consistent.
Yes, but my point is that even though you arrive with consistent theory, but that looks very radical, there will be, of course, a resistance in the physical sciences because a radical new point of view. We are conservative as an experimental scientists. We don't want to invoke new things unless we really forced to, right? And it's not like I'm sitting down and thinking about new crazy theories every day. So, but finding these two new phenomena that the GR could explain better was very important for the whole physical world back then. All right, so now I will stress out in these two slides why it's important to understand where we have working tests of GR and how we should avoid comparing apple to oranges. Because in literature, in modern literature, especially in cosmological literature, I'm not aware of more about pure GR literature, many authors say, okay, we have tested GR very precisely on the scales of the solar system because there's a solar system, few astronomical units, all these compact binaries of neutron stars are also few astronomical units. Gravitational waves are emitted from the coalescing blue black holes, are also very small systems. And then we extrapolate the theory to the size of the Hubble horizon. Well, the scale length is not the only scale of the theory. Because we can have two different natural scales for the GR, which is a metric tensor theory, will be a curvature scale and potential strength scale. And I'm going to give you examples for very simplified from the Schwarzschild symmetric metric, because these objects are more complicated for more complicated metrics. But nevertheless, you can construct something we call Kretschmann scalar, which is a contraction of the Riemann tensor that can be thought as a measure of the local curvature of the time-space. And of course, you can use Newtonian potential on the body on the circular orbit around another body as a strength of the gravitational force potential, the dip of the potential well. And these are not two the same things. And how is that? Well, this will go, and of course, sometimes we have, well, not sometimes, many times in the literature, we have many papers claiming, okay, we test GR in this scales. But of course, the authors give a length scale, but this can correspond to different curvature scale and different potential scale. And why this is important? This will become apparent very soon, just by studying this diagram. Here I put a potential in this normalized unit by c squared and the curvature. So you can see, first of all, the curvature can span nearly 50 orders of magnitude, conceivable curvature scale in the universe. And we have various astrophysical bodies that test GR on this diagram in different places. So for example, we would have a solar system planets motions here on this line. This would be sun. We would have a satellite galaxies here. This would be white dwarfs, already high potential, high curvature. Neutron stars and black holes are here. But for example, supermassive black holes, they have the same potential comparable to 1. Super relativistic potential as the small black holes, but the space between them in curvature is 20 orders of magnitude. That's why if you fall into a supermassive black hole, you won't be spaghettized. You have a chance to survive falling in the inner event horizon of the supermassive black hole and have a chance to see what's there. But when you fall into the solar mass black hole, you're going to be killed instantly because the tidal forces are much larger, because the curvature scale is also much larger. Then you have Milky Way and some other galaxies. So these three horizontal lines describe the three separate regimes of the history of the universe. So this is Big Bang nucleosynthesis, so very high curvature universe. From this to this, you would have, of course, in different potentials. If you have primordial black holes, you will still have black holes here. Then the last scattering, so this is when the plasma CMB happened. And then finally, the acceleration scale, which is the lambda. And funny enough, if you see that if we account for the scale in curvature and potential that will be responsible for the accelerated expansion of the universe, then we have this line. And you see this line goes from the high potential to growing curvature, but there are not many bodies when we can actually test this, except from galaxy cluster, maybe, and galaxies themselves. And these are the equivalent diagram for the experimental tests we have. So this point of the parameter space was tested by the post-Newtonian constraints. For example, inverse square law testing in atoms, or this is from solar system motion in bodies and our probes. This should be tested by LISA. So if we're gonna launch the gravitational wave observatory to space, we're gonna have a chance to check out this portion of the parameter space. So this is now being tested by advanced LIGO, so gravitational wave from black holes and other bodies. So this is Sagittarius A star, so black hole we have in our own galaxy. So some other observatories could test here. So this is the Einstein Event Horizon Telescope, so something, the first picture of the black hole. At the same time, we only have a small portion here tested by the Planck satellite using CMB, mainly by testing how many tensor modes you could have in CMB, so what are the primordial gravitational waves. And we have future facilities that will test, map galaxies to the largest extent of the universe, and will test phenomena like baryon-acoustic oscillations as features in galaxy distribution. I would like you to pay attention to this huge parameter space desert. So we have nearly 20 orders of magnitudes in curvature that has not been tested and experimentally. At the same time, we can hope that incoming large-scale survey of the galaxies of the grandest scales, like Euclid satellite from European Space Agency, or DESI mission, LSST mission led by Americans, also Square Kilometre Array, all this big, grand, multi-billion-dollar campaign to map the universe on larger scales will help us to put some test here of the theory. But we're still going to have this problem with the huge parameter space deserts. Well, there's also extra intergalactic uncharted territory when you consider what happens in between galaxies, like in cosmic voids. And some of the tests I will show you at the very last slides of this talk should provide us with extra data points in this regime. Because they would not only convey in galaxies, but also some higher order of galaxies involved in their velocities. So I hope I convince you that even though GR looks it's a very nice, beautiful theory that works great, it hasn't been tested in all extent to its parameter space. There might be a new fundamental theory that predicts that something else happens in the vacuum when there's very low curvature and very low potential. So it's very, very important to convey test of this of GR itself. And cosmology is the only hope for us to probe this parameter space here. Okay, so now we have GR, of course, but we would like to know also what are possible extensions of GR, even if they are only phenomenological. They are not fundamental new theories of gravity, but they can predict something else that could happen in the universe, and maybe by testing this, we can find a way to help theorists convey new fundamental theory of gravity. This is our phenomenological modification of GR. So I have written Einstein-Hilbert action with some extra terms here. So all of them need to have GR curvature term, and of course all of them need to have particle physics and dark matter. Now, if you have nothing here, you don't have acceleration of the expansion, so this will be Einstein de Sitter old model. Now GR, because you need to have stuff that accelerates the expansion of the universe. So no acceleration, GR has this, Einstein cosmological constant. You can have modified gravity in many different ways. You can put an arbitrary functional of the Ricci scalar. You can have higher order derivatives. You can have only weakly coupled scalar field that doesn't couple to matter, but just couple to metrics. So with its potential, this will be then called dark energy. But most of these theories, except this one, which doesn't couple to matter, predict extra degrees of freedom above the degrees of freedom we have already in GR. And whenever there's something like that,
just a single degree of freedom, yeah? The scalar field.
But for the most scalar tensor theories.
Because it is thin. Yeah?
Of course.
Absolutely no hint.
Well,
I claim to speak about experimental science.
well, I didn't put.
This has nothing.
The scalar vector tensor theories are up there as well.
The formulae are relatively simple. We like Klein-Gordon, therefore maybe not linear Klein-Gordon if V of phi is not quadratic but more complicated, but it is just...
Well, if you can give me a new fundamental theory of gravity that would work on cosmology and would be scalar tensor, not a scalar tensor, a vector tensor. There are vector modification as well. I would be very happy to put it on test. Not only aesthetic, I think you will see in a moment that it's very hard already to, with this simple only scalar field, to test one theory at a time, because there are so many of them, that is basically would take infinite amount of PhD students with infinite amount of grants to convey tests of most of these theories. So we have to simplify, of course. And this is what I'm saying, clean to you. This is phenomenological approach. I still want to test GR, but I want to have some extra alternatives to be able to see in which regimes, if there's something else than GR, we can expect differences.
The derivatives also covariant.
Yes. So all these theories that predicts extra degrees of freedom would produce
For the scalar field, it's the same.
non-negligible fifth force. Whenever you have a gradient of the scalar field, for example, and if scalar field is coupled to matter, you have a fifth force. So different force than four fundamental forces we know in nature. Effectively can be modeled as some kind of enhancement of the local gravitational forces. And now this is the trick, because if there's a fifth force, of course, you can say, well, this theory is not valid because the Newton theory works well for launching satellites into orbit. GR works well to explain everything in the solar system. There's no fifth force. Of course, all these theorists knew about this, and while they work about all these theories, discovered a few very interesting nonlinear mechanisms that are called screening mechanisms that help to either suppress this extra degrees of freedom locally, or hide them from the visible sector. So we have to have a working theory that also accelerates the universe, but would produce different growth rate of structures. So this fifth force is important, because if I have a theory like that basically, in its simple form, predicts the same as GR. This is like, this is tautology. I increase the complication of the theory, but I don't predict anything new. So I think this theory has a null value. So at least I want to predict new phenomena. So if you have a fifth force that work on cosmological scales, you will produce different growth of structures, galaxies, and so on and so forth. So very quickly, these are two very complicated mechanisms, but generally speaking, there are few of them families of this mechanism. Two very most popular are some called chameleon screening family. In this theorist family, the fifth force is suppressed by something we call chameleon mechanism. A chameleon mechanism, I will say a few words about this just in one slide, is a mechanism that change effective potential of the scalar field with connection to the local density. So when they have a very dense regions of space, the effective potential goes up, so the mass of the scalar field also goes up, so if fifth force is suppressed, if it's like a Yukawa-like coupling. When the local density is low, then the effective potential can also go low, so that you can produce a significant fifth force. So this means here in this mechanism, the suppression of the extra degrees of freedom is environmentally dependent. So you break superposition principle, for example, because it makes difference if you do the same Galileo-Pisa experiment, but you put the Pisa leaning tower into the cosmic void. Then you have extra force accelerating the balls dropped by Galileo. But if you do it on Earth, in our galaxy, which is high density region, you get full Newtonian limit. Another interesting mechanism is so-called Weinstein mechanism, which is invoke higher order derivatives of the scalar field that suppress propagation of the scalar field degrees of freedom in the vicinity of massive bodies. Here, it doesn't matter what's your average background density, just what matters is the mass of the body and the parameter of the theory that grows the universe called Weinstein radius. So for example, if you farther away from the sun than its Weinstein radius, every object has its own radius, you would feel extra acceleration towards the sun because of the scalar field. But if you're closer, you won't. And of course, it happens that most of these valid theories have Weinstein radius for our galaxy to be larger than our galaxy, a few times larger. So it means that the kinematics of the satellite galaxies wouldn't be affected by. But the faraway galaxies will already feel the extra force from Milky Way, and then you will have this growth rate of structures different. So I think I will skip the explanation of the Weinstein mechanism. So the problem is there's so many ways to really self-consistently, effectively, or phenomenologically modify the gravity by just adding something to Einstein-Hilbert action, and then just, you need to take care of two things. First, that the theory is stable, and then second, that theory doesn't have Gauss, which means it doesn't predict negative kinetic energy states, because then you run into huge problems, and then your theory couldn't explain the observed universe. So there are theories that are no local gravity or higher order derivatives, new degrees of freedom, higher dimensions, generalization. So not all of them are only simple scalar field theories. Some of them are more complicated. The problem is that we cannot sit down and make a scenario that we're going to test every of this theory one at a time, because there are too many of them. The parameter space is huge, and most of these theories not only involve one new number, they actually involve, for example, functional, which is infinite, nearly new infinite space of theory. So my approach is the following. I don't want to sit down and, I mean, this is theoretist work. They bring model builders. They bring to us to the table interesting theories. I try to categorize them to some possible, as broad as possible general categories, see what kind of a different effects they would predict I could measure in cosmology, and then, of course, work back to theory saying, no, your theory is wrong because it cannot explain observed galaxies. The situation got quite better thanks to the observation of gravitational waves. So this is like Pandora box of modified gravity. So we now, especially of the multi-messenger. So the kilonova, very famous event when there was a coalescence of two neutron stars observed, which is important because at the same time we observe electromagnetic signal and gravitational wave signal. And some of these theories predict that the speed of gravitational waves would be different than the speed of electromagnetic waves. That's called disformal theories, when the coupling is disformal to the metric.
Just a minor remark that I have proved many years ago that those higher order theories are equivalent to extra degrees of freedom theories.
Thank you very much. So after this observation, well, we have a little bit clearer stage. Just to make a very quick comment. The fully unambiguous modification to gravity would consider tensor propagation structure. That should be different. But this would tell us, as I said, that the gravitational wave propagation would be changed. So after the gravitational wave event of this, and also was gamma ray bars counterpart, I would say fully modified gravity is dead. Because what is left, this is something that gravitational waves and kilonova did to us, it's only this side of the diagram, which with conformal coupling to metric. So all this formal coupling, which actually were physically more interesting theories, are now falsified, not admitted by the real universe, and we just can focus on this. There's still plenty of the theories. Of course, general relativity is here to test. Nevertheless, we are already moving forwards, making things a little bit simpler. Okay, how one can test this scenario when you have some exact degrees of freedom, not necessarily coming from the new fundamental theory, but some effective field theory that would change some parameters of how the structures grow in the universe. So we start from initial conditions, and of course we have only one universe to observe. So in particular, to model, understand what we observe, we need to rely on the next best things we have to the real experiment, which is Gedanken experiment, very sophisticated Gedanken experiment, so Einstein thought experiment. When we caught all known physical laws that are important on those scales, and model the evolution of structure in the growing and accelerating universe over 14 billion of years of evolution in the supercomputers to try to understand the picture we observe here. Now, by changing this, but we know this is like forgiven initial condition, and changing the laws of physics on the way, we can test different theories, at least in some approximate manners. We can see what kind of observational signatures you could forest in these new theories. And this is the standard paradigm now in cosmology. So this is plot I had in my PhD thesis, so more than 10 years ago. No, roughly 10 years ago. It comes from the embodied simulation when I had, this is like final redshift 0 snapshot of the some universe, density field of dark matter, for simplicity. So the density contrast, something that tells you how much the local density deviates from the background average density, it's called density contrast in cosmology, can vary from 1 to million, which means a huge dynamical range. So in cosmic voids, you can have negative density contrast, so local density is below average density. Inside this agglomeration of mass, like galaxy cluster, you can have millions of local density. So it's quickly apparent that you cannot just rely on perturbation theory because the galaxies form in the highly nonlinear regime. So you can quantify these differences in the density field by just measuring Fourier power spectrum of this density fluctuation. Delta is the density contrast. You can measure this and you can express this in some ways, like a K-dependent scale. And to understand how, at least on the linear level, these fluctuations grow in the universe, you can consider linear evolution equation for this density contrast. When here you have a Hubble dragging term, and here you have a sound speed, so basic pressure term, and the gravity. So for dark matter, pressure is 0, but for baryons, it would not be 0, and then can foster some simple solution for growing modes on the larger scales. I'm mentioning this because on linear level, you can think of this very special parameter that is nowadays a holy arc to be measured by all these multi-billion observational campaigns. It's called linear growth rate. Basically, this function f is a logarithmic derivative of the growing mode solution of this partial differential equation with respect to cosmic time. This parameter, if this parameter tells us how quickly, how effectively structure grows in the universe on all scales. And then later, of course, you involve simulation to see what happens inside galaxies. So, of course, now I don't have much time left, so let's say in 5 minutes, I will show you, even though many models will predict huge differences. For example, in this plot, I considered some modified gravity model which actually I helped in my PhD thesis to falsify, but back then it was still fashionable, with some scalar field with screening. So this is GR prediction, and then some different variation of this modified gravity will predict much stronger clustering, which means they will predict differences in this power spectrum. And I helped to falsify by showing that this is incompatible, for example, with the observation of the local group of galaxies. But nevertheless, this is one of the possible ways. So, for example, taking a different modified gravity model, which is still in the market, it's called Dvali-Gabadadze-Porati model. It's a brain model, basically, in which if you go down to lower dimension, you have a 4-dimensional brain embedded in 5-dimensional bulk time space. And all fundamental interactions except gravity and all particles that belong to standard model of particles are confined on the brane, but the gravity can leak out to the fifth dimensional higher space. And of course, this brane can bend, which is you have an extra degree of freedom, which is scalar field. And one of the variations of this model is called NDGP. And basically, what I plot here is the power spectrum of the density fluctuation in the GR and two variations of this model. And to actually, because it's log-log plot, because we have so many scales of magnitudes in cosmology, I give you also for the reference the relative ratio. Well, great, nearly 20% difference from some of this model with respect to the GR. So the clustering should be much higher. But if you have a higher clustering, how you can measure this? Because you can observe dark matter. This is only simplified simulation. Well, we know the phenomenon, which is called weak gravitational lensing in cosmology, that can directly measure this, quantify these fluctuations, because gravitational lensing reacts to matter fluctuations on the line of sight between the observer and the lens. So if you would have endless void, and this would be some galaxies, which are spherical, just for the sake of argument, and then you have put a strong mass concentration, these galaxies would be lens, so the abruptness would be increased. You can also measure the shape deviation. Basically, this effect is, of course, very small. This is over-exaggerated by many orders of magnitude. But if you measure thousands of galaxies, you can make a statistical measurement of this power spectrum. Now, but there is a problem, because GR tells us that there's not only dark matter in the universe, and there's also baryonic physics, which means the gas, interstellar gas, all these galaxies were shiny bodies of stars, and they're also massive. And on those scales, when this is relevant, baryons are also important. And because lensing corresponds to the total matter, not only dark matter, we need to consider baryons. And when you do this, and you do this with self-consistent, with modified gravity, you immediately see there's a huge problem. We call it the baryonic degeneracy. So this is the same fractional matter perspective like here, more or less, for a little bit different family of modified gravity models, but this is not, effect is very similar. Naively, what you expect for dark matter only simulation, you see the thick green line. So enhancement, also 40% of clustering at some scales greater, or maybe for weaker model, 20%. Now, but when you do the simulation with baryons, when you allow the baryons to condense, form stars and galaxies, and then in this, some of the galaxies would be supermassive black holes that would turn on the AGN, active galactic nuclei. So very powerful disturbers on galaxies that make the gas go around the galaxies, expel the gas, and so there's this much more complicated vicious circle of gas accretion and ejection. Then you get these thick dotted lines, which means that how strongly this nonlinear physics of galaxy formation gives you effect that is opposite direction to the modified gravity. And because we don't know from the first principle how this effect should be strong, this baryon physics, basically they're too degenerated. So in the worst case scenario, you could predict this model, which is fully modified gravity model, but if you include baryonic physics, you would predict the same effect as GR to some extent, with some weaker baryonic physics like here. So complication. So what you do next? I skipped this slide. Well, you can go look for looking galaxies. If you cannot measure this in the lensing, total matter perspective, let's see if the clustering of galaxies can be used. The problem is that the galaxies are not faithful or unbiased traces of the density, because galaxies do not form everywhere in the universe. You have to be on the peak of the density fluctuation to form a galaxy. So this is one-dimensional universe. Let's simplify this. You have a large-scale perturbation of density. This would be cosmic void. This should be some galaxy cluster or some high density. And then, of course, you have many small fluctuations. But then there's a critical threshold for collapse. Because the universe is growing, not every perturbation can collapse and form bone structures. Because if the perturbation is too small in the density, the expansion of the universe will win, and it will never form bone structure. And of course, galaxies need to live in the gravitationally bound structures. So only on these peaks, you form galaxies. Sometimes you over peak, but you are actually in the local underdensity. You also won't form galaxies. So this is complicated picture, and this is well illustrated by the simulation by my colleagues from Durham, when they took the local group, assembly of the local group of galaxies, and we did the simulation with dark matter, baryons of stars, and so on and so forth. So this is what the GR, or most of the models would predict the sky should look like if we could observe dark matter. So there's plenty of small dark matter, we call them halo structures, but this is the same part of the simulation, but we only render stellar light and gas. So basically you see that there's a completely two different universes, and this is what you can observe, and this is what you can easily predict. It's very hard to predict this part. So another effect is very important when you take the galaxies. They're not only biased, so they not form everywhere, but we don't observe three-dimensional position of the galaxies. We only can observe in a very straightforward manner two positions on the sky. So declination and right ascension. So very precise we can say when the galaxy is on the sky, but how to get the radial velocity is much more complicated. We do it measuring the spectrum of the galaxy, and then we find the recession velocity. We use this recession velocity and the Hubble law to get the radial distance, but the problem is the galaxies have also extra velocities due to the local gravity. This causes something we call redshift space distortion. So because galaxies also move to the local gravitational field, when the local gravitational field makes the galaxies are expanding, so in real space you see expanding sphere, the observer is here. But the redshift space, when you change the radial distance to the galaxy to this spectroscopic measurement, you will see a flattened sphere. When you have a turnaround, the density starts to collapse, you will see completely degenerate, squashed circle. In the nonlinear regime, when the things are collapsed, like in galaxy cluster, when the initial potential energy was exchanged to the random motions, you see elongated structure on the line of sight, which we call finger of God. This leads to the picture like that, where this is the SDSS longitudinal sky survey observers in the center. If you zoom in, you see all these elongated features of galaxies. They are not real features in the universe. They are just artifact of the fact that we don't observe the radial distance to the galaxy without this component of the local velocity. This means that if I have a theory that predicts this, which is the clustering of the so-called real space, I need to have a mapping that would translate this prediction to something that can be observed, the redshift space distribution of galaxies. When you have these fingers of God, these extra effects that voids are squashed. This is done in a very simple manner usually. Well, it looks complicated, but they are simple mapping. You map the observed power spectrum clustering and divide it to the two different components. Large-scale structure deviations, that would be the squashing effect, and small-scale structure effect due to velocities, which is damping of the structures on the small scales by the fingers of God. This is a complicated model. It takes galaxy biasing into account, some of the local velocities. But finally, if you have this model, you can, measuring this, say something about cosmology. You can say something about the power spectrum and this growth rate, which appears here. And often you see this in the literature, that someone goes, takes some different galaxy redshift survey and put a data point on this chart. This chart is the following. This is a redshift, so we're looking back in time, or the higher the redshift, the farther away we are from the observer. And we have this growth rate normalized by the galaxy bias, which is unknown. So this is F sigma 8. Sigma 8 is a normalization of fluctuations to compare different galaxies as well. And the thick black line is the GR prediction. And there are many data points here with huge error bars. But some people will say, okay, this F of R modified gravity already predicts this line. Well, it's in trouble because this is already 2 sigma deviation. Well, of course, error bars are really large here, but still, people use this kind of observation to say, okay, we falsify modified gravity because we measure the growth rate is consistent with GR, not with this, your favorite modified gravity. So you need to change the subject or go to quantum physics, for example. Well, wait a minute. I said you that you need this complicated mapping model that connects the prediction by the theory to the observations. And all this underscored by orange line components actually depends on your model of gravity because it's not self-consistent. Because the modified gravity galaxies can have different bias because the collapse threshold will be different. They also foster different growth rates, so different velocities. So actually, what you really do if you do back of the envelope calculation and go try to develop your own modified gravity self-consistent model, your data points will move because they are not absolute data points. They are model-dependent data points. You measure something, but to put it on the diagram, you need to assume some model of gravity. And we did this test for this DGP gravity, so this higher dimensional gravity. So what we plot here, this is some cutoff scale, how precise your galaxy clustering catalog is. So this is, you can measure galaxy clustering on very small scales. Here you can measure galaxy clustering on large scales. This is the input growth rate we did inject in the simulations. And we took the two different redshift space distortion models, one for GR and one for DGP. And we do the blind test. We took the modified gravity universe, but we only use GR template because observers only use the one GR template, so GR modeling. And you see data points are shifting. And these are 3 sigma error bars, not 1 sigma error bars. So this is actually 2 sigma error bars. But you see, at present, if you have a large error bars, you can get away with using the wrong template because the growth rate was here and GR template was giving the lower prediction, even though the real value is the black line. And the correct template that takes into account all these complicated effects gives you right value. But if you go to the future surveys, all the surveys that claim to measure dark energy or test GR with the great accuracy like Euclid or DESI, you will have this situation. If you use the wrong modeling, you won't be able to discover modified gravity, even if the real universe will be modified gravity. So this is very important to be self-aware how to test it. There are many different problems, so just summarizing this with one slide like this. Even though we need to test GR, and there are many possible tests to do it, there are also modified gravity theories on the market, this is a very hard task. If you go to one problem, is a theoretical bias proneness. So this is this kind of effect. If you use the wrong modeling, not self-consistent modeling, you signal data, you reduce from the observation, depends on the model you assume, model of gravity you assume, for example. So this consists weak lensing because it's also assumed gravity, residual space distortion, on cluster mass comparison. There is also baryonic degeneracies because it's very hard to model baryons. They are not very cheap, this simulation. Only can make one simulation maybe for lambda CDM. It's very hard to make it one for one modified gravity model. And this affect different systematics. So what to do? I mean, should we sit down and cry? Of course not. We are brave physicists. So in the very last few minutes, really, trust me, there's only 2 or 3 slides left. I'll try to advertise one of the things I found recently, going back to the works even of my late supervisor, Professor Juszkiewicz, interesting observational statistics that can be, I think, used with success to convey this test, avoiding most of these problems. It relies on the following observation. So as I told you at the beginning that one of the core assumptions for our universe is that all the structures that we observe today grew up from the initial adiabatic Gaussian fluctuations. So if you have a Gaussian density distribution, it looks like this. Of course, because the gravity works toward nonlinear clustering, this would produce departures from the initial Gaussian distribution. It's very simple to understand why, because if you consider, so this is delta plus 1, so let's say density contrast, so this value equal to 0 means you're in the cosmic void, there's no density. So if you have initial density distribution that is Gaussian, you start to produce clusters, galaxy, dark matter halos, so you can grow to arbitrarily large density contrast in this direction. While here, you can only get empty space, so there cannot be delta lower than -1. So this naturally produce skewness and kurtosis, positive. Gaussian clustering make the departure from the initial Gaussianity towards only this one direction. And actually, how strong this departure is depends on how strong growth of structure is in the universe. So this is a simple example from one of our papers. We consider not only skewness and kurtosis, we consider the first 5 moments. So variance is very simple, it's a power spectrum. But then there could be skewness, kurtosis, and the 5th moment. So these are connected central moments, which means I subtract the Gaussian expectation. That's why there's this extra terms here. So C stands for connected and for central, and the whole expression is for connected, which means I remove Gaussian expectation. So the naked values of these parameters already tell you what a departure from the Gaussianity expect from variance, because variance is not a measure from departure of Gaussianity. So if I take the density fields of simulations, I can see there will be variation. But this is already just self-consistent test because I show you the power spectrum already effect. But I cannot use this test because we don't observe density field directly. But what happens if you go to galaxies? So this is the plot that we already have published 3 years ago. And I have a newer version of this plot, unfortunately not in this presentation because it's still under embargo on the paper of the DESI Modified Gravity Consortium. But you will have to believe me, because this is more or less survival. So the new plot will also include residual space distortion and galaxy biasing. So here we took only galaxies, we modeled galaxies in our simulations, and consider this SNs. So this take nth central moment and scale it by variance. Scaling by variance is very convenient because the variance is basically at different redshift, tells you how the structure grows on all scales. So this is called something we called clustering amplitudes. So the values of this will tell you how much your galaxy distribution deviated from Gaussianity. And I already plot here the difference with respect to GR. And by the way, I never said that before, but whenever I say GR, I mean non-relativistic limit of GR. Because in cosmology, we only use GR because the field, this divided by square, is much smaller than unity. Actually, it's of order to 10 to minus 6. So I can fully say that all relativistic effects are not important, at least on those scales. So this is departure from standard gravity growth rate of structure. So this is the S3 skewness, kurtosis, and the fifth moment. This is very noisy, depends, and this also depends how many galaxies you can observe. This is very complete survey like Euclid. This is something you can expect on, let's say, current state-of-the-art the galaxy survey like SDSS. So there's some effect already interesting in skewness, but I would like to pay attention to kurtosis. There's a huge effect, and the shaded error bars are conservative cosmic variance errors, so actually larger than even the errors from the sampling here. So this is few sigma effect if you go to the higher order moments. So at the very last notice, I say, wait a second, do I try to trick you again? Because as I said, this was for the real space. So we did the modeling already for redshift space, but I cannot tell you the plot yet. But the plot is very exciting because this effect still persists, which means we can go now, wait for the Euclid data, do this test, and we're going to have 4 sigma tests of GR on cosmological scales. But to understand why this is not so strongly affected by the GR is the result of Shivon et al. Paper with my late supervisor, Professor Ruszkiewicz. Basically, the skewness, for example, this first moment I consider, in the real space looks like this. So this depends on some value that is predicted from the Gaussianity, and the effect on the cosmology is here. This is the effect of the power spectrum. Now, in the redshift space, there's also effect on the power spectrum, but this difference between these two is very small. Because there's this very surprising conspiracy that this term and this term to the n to minus 1 power are affected by all these nonlinear motions of galaxies to the same extent. So they cancel out, not perfectly, but to the high extension, which means I can now go, and this already shows the galaxy bias also, because the FX appears for all different galaxies as well. So now I can go and forget about this complicated modeling. For every single model, I need to derive my modeling between observation and theory. Just use this, exploit this dependence, and do nearly model-independent tests of gravity based on clustering. So we hope to convey this test in years to come with the growing team. So I will leave you with my conclusion and take home messages. And sorry for running 6 minutes above my 50-minute time limit. It's crucial to test GR on cosmological scales because the theory has a huge parameter space in curvature and potential. To obtain clean test, both for GR and modified gravity, is very hard because all these various degeneracies leading to systematic effects. We try to occlude for difficult clear methods like velocities and hierarchical clustering in redshift space distortions. But I think the really final answer to this question will be that convince many people that if we do modified gravity galaxy formation simulation, so the one that can predict this beautiful star and dark matter differences, that would basically fill up the last missing puzzle. But I hope to get a very convincing evidence from the higher order clustering moments I show you here. Thank you very much for your attention. I'm happy to answer all your questions.
Okay, thank you very much. We still have time for some questions or comments.
So I'm very much impressed about those ideas to search for modified theories of gravities. I know that for cosmology you don't care so much about very, very tiny objects, but if you were asked which of those directions to modify gravity would be the most compatible with quantum gravity and quantum effects?
Well, if you can tell me what's the quantum gravity, then that would be a starting point. I can tell you only that there is a quantum aspect to this, because I didn't have time to mention there's a laboratory test of all this theory. Even though they have screening is not perfect. You can create a very strong vacuum in the laboratory and assume some of the theories don't feel the presence of the background density. So for example, ultra-cold atoms, ultra-cold neutrons are tried to be used as a test. So then you need to go to and then actually, I know of some of these theories predict differences in the waveforms of some particular quantum system setups. So this is the only quantum aspect I know. Quantum gravity, well, I would say, because my standing is the following, and I'm going to be very brutally honest with you. All these models have the same problems to be quantized as GR because they are just effective field theories. As I said, to be really honest, very important thing. Very few papers of modified gravity, except for example those I wrote, but I'm aware of this, say the following sentence. But they should say this at the very beginning. We assume that by unknown symmetry of something, the true Einstein constant is 0, and then we have modified gravity. Because all of these theories also include lambda, because lambda is just an integration, constant of integration. So if you modify GR and add, like f of r, this extra functional, you can still add lambda. So they would say that lambda is 0. So the argument is the following, which I'm not fully appreciating this argument. They say that it's easier in physics to make something 0 than something very, very small. Because real lambda is 10 to minus 26 kilograms by square. So my approach is different. I try to narrow down all the possibility for all these theories that are left using observation. Because once we arrive, okay, now GR being tested in the black holes, solar system, and now if we can convince people that the GR was also very well tested in the intergalactic scales, the space for this model will be growing smaller and smaller.
Okay, so this summer I attended actually a conference, and I attended a number of lectures on these small scale measurements, and basically the conclusion is that up to 10 micrometers Newton's laws are satisfied. However, the smaller we go, I'm not talking particle accelerators, already at nanometers, the knowledge is very poor, and at particle levels, the relative error could be of trillion%. So even the gravity could be million or billion times stronger or weaker, and we wouldn't know. However,
it's easy to understand because the gravitational force is 10 to the 40 times weaker than the electromagnetic force, for example, due to particles.
yes, so indeed, I think there is still a lot of improvement to be done in, like in nanometer scale, even. Like,
Don't
for example,
tell it to these modelers because we have more models.
Quantum aspects of gravitational field, which is still classical, or does it really include quantization of gravity?
I think it does include quantization. It just look for quantum effects of classical field.
It's not quantum gravity.
It's not.
Okay, last question.
I think that was why. Okay.
Just for the sake of the colloquial nature of this colloquium, Jurek, that's the question of you. As a person grown up in Chorza, which is very much mathematized place, I always believed that the main quest for general relativity was just to write a Lagrangian. To which extent it was really driven by the observation by Einstein and others that this Newtonian approach and the notion of inertial system is not really consistent, because actually Newton had the elevator experiment, but in modern language, if you look on the videos made on International Space Station, it looked very much like in the inertial system, but yet it still falls with the acceleration to in the direction to Earth, right, with the radial acceleration. So which those two ideas were prevailing, so to speak? It's very much clear that Newtonian theory is and Galilean equivalence principle is inconsistent from the very beginning, with observations, right?
Mm.
So was it
No,
really a
yes.
driving force, or just it's a legend that Einstein was disturbed by this observation, and that's why he thought that he has to invent something better, a theory which would accommodate inertial, consider equivalence of all coordinate frames moving with arbitrary acceleration.
You mean he arrived at strong equivalence principle? Yeah. It's hard to say because Einstein is dead.
How historically it looked like?
Historically, he was at a certain moment he was convinced that there is no way to to discriminate between acceleration and gravity. Yeah. That's all. No.
And the argument is pretty simple, right?
But we know it's wrong because we can distinguish between acceleration and gravity, because gravity produces potential, and potential change the vacuum states, for example. So there is a way now.
Many times. I have such a book classical papers by Einstein. So he repeats many times this point of view.
Okay, we can continue this discussion with cookies and coffee. Thank you very much once again, Wojtek.